Hello and welcome back to another video on icing. In this video we're going to talk about structural ice. More specifically, we're going to work our way through the physics of icing. So in previous videos we talked about the requirements for icing, and also we talked about what is exactly supercooled liquid water and where we find it. In this video we're going to talk about the accretion or the collection of supercooled liquid water on different structures. So, in general, how do airframe structures accumulate supercooled liquid water? So here we got an aircraft flying through a cloud. Those little droplets are cloud droplets. We're going to look at a wing, the wing of the airfoil, or the airfoil of the aircraft, I should say. And specifically, we're going to define the collection efficiency as the ratio of the water mass that strikes the airframe to the water mass in the free airstream. So the free airstream, what exactly is that? The free airstream is the geometric area that's swept out by the wing. So if you look at the thickness of that wing, then that distance defines the free airstream. In other words, the air that's approaching the wing and that should normally strike the wing. But not all of those droplets out ahead of the wing that are in between those two lines out ahead of that wing will strike the wing or the airfoil. And the reason for that depends upon a number of things. It depends upon how big the drops are, depends upon the type of airfoil, and also depends upon how fast that airfoil is going through the air. So let's take a look at the drop size first. So here we have two wings, and we're going to be flying through a cloud at the same speed for both wings, and we see two different drops. So all the conditions are the same except for the drop size. On the bottom you've got a small drop, on the top you've got a big drop. With the big drop has a lot more mass, and mass times velocity gives you momentum. In other words, the inertia of the drop. So big objects tend to keep moving forward because they have momentum. Just like a big garbage truck keeps barreling down the street, it's hard to, or a semi or something like that. Something that has a lot of mass, has a lot of velocity, has a hard time changing direction. So these big drops keep moving forward. Even though the airflow around the wing diverges around the wing, those droplets don't really follow those streamlines. Instead, they cross the streamlines and they strike the wing or the airfoil. So as a result, they have a high collection efficiency. On the other hand, if we look at these smaller drops have less mass, and mass times velocity gives you momentum, which means they don't have much momentum. They have much smaller inertia. So in other words, if they weigh less and they're moving at a certain speed, they will tend to be deflected more. So as a result, they tend to follow the streamlines around the airfoil because they're more easily deflected. So big drops tend to cause a much more higher collection efficiencies, which means severe icing. Small drops tend to produce less icing. So wherever you see a lot of ice, typically that also implies really big drops, bigger drops. The other thing that determines, the second thing that determines the accretion of supercooled liquid water on an airfoil or a wing is the size and shape of the wing itself, and not necessarily just the wing, but also other things that are sticking out into the airstream. We're going to stick to the airfoil analogy in this discussion, but at the end we'll look at some pictures of things that stick out into the wing that stick out into the wind or the air that aren't necessarily wings or airfoils. So we are flying through the air. We've got two different airfoils, one that's really fat and one that's really thin. Drop sizes are the same and the airspeeds are the same also. So the only thing different here is the airfoils. So if you have a very thin airfoil, the air is not deflected as much around a thin airfoil. Notice that the streamlines are pretty close to the airfoil itself. So because of that, the droplets follow the streamlines and they tend to strike the airfoil because the droplets are not disturbed or pushed away from the airfoil itself. So objects or airfoils that have less curvature or very small objects tend to have a very high collection efficiency. They get a lot of ice. However, things that are a little bit more curved, things that are fatter wing here, objects that are more kind of blunt, tend to push the air out far away. In other words, you get a bow wake and then the disturbed streamlines around the wing. Results in droplets that follow the streamlines. They kind of move away from the wing, and as a result, you have low collection efficiency. So smaller objects, things that stick out into the air, or blunt objects, or more pointed objects, I should say, tend to have a much higher collection efficiency. And here's some pictures of some icing research that we did back in the 2000s. You can see, one of the most pointed objects on the airplane, of course, is the nose. This is a Hawker 800 XP, and you can see a large chunk of ice that formed on the nose of this aircraft. And then other objects, such as antennas that are sticking out into the airstream, tend to pick up a lot of ice. You can see this little protuberance coming out the bottom side of this airplane picked up quite a bit of ice. Other things that tend to pick up ice, remember that the horizontal stabilizer is kind of a small, thin airfoil or wing, much smaller and much thinner than the main wing itself of an airplane. So you tend to get ice forming on the empennage, on the tailplane, a lot sooner because it has a lot higher collection efficiency than it does on the leading edge of the wing. If you see ice on the wing, you know you got a lot more ice on the tail. And then finally, the airspeed determines how supercooled liquid water is accreted onto the aircraft or the structure. So generally speaking, the faster you go, the higher the true airspeed, and the greater the collection efficiency. If you think of it in terms of momentum once again, droplets that are moving faster have a higher momentum, and they tend not to move out of the way more as easily. So they will have a much greater collection efficiency the faster the airplane goes through the air. Whereas if the airplane's a little bit slower, if it goes slower, then it doesn't have a very high collection efficiency. And the reason is because the droplets are moving slower and they have less momentum. So for low airspeeds, slow airspeeds, the collection efficiency tends to be lower. Now this is assuming that the angle of attack is the same. And generally when you fly, that's not always the case. But in this case, in our example here, if it's the same angle of attack and you're going faster, you tend to get a higher collection efficiency. The problem is usually when you fly and you want to go slower, if you're going slower, that means you lose lift, so you increase your angle of attack to increase the lift so that you can maintain altitude and fly at a slower airspeed. Well, when you increase your angle of attack, that means that it's allowing the airflow to strike the wing in the bottom, and you tend to collect more ice on the bottom of the wing. So you have a higher collection efficiency. But generally speaking, high collection efficiencies happen with large drops, thin airfoils, and faster airspeed. And low collection efficiencies happen with small drops, thick airfoils, and slow airspeeds. And to summarize that, I've got one graphic that shows the high collection efficiencies and low collection efficiencies for drop size, geometry, and also airspeed. So I hope you enjoyed that video. The next one we're going to talk about, once water accumulates on a wing, how does it freeze?